So we are started today. Want to make sure you can hear me. So we'll give a couple minutes here for people to jump on. All right, excellent, thank you. So do we got any questions before we get started? All right, so looks like the audio is working well. Looks like we got people. So while we wait for a couple more people to join, what I'll do is I'll go ahead and come in here. So we do have a question. I thought this question would probably come up, and that is, do we still have a test on Monday? So what I thought we could do is push the test back till Wednesday. Usually people don't have any problem with that. And that will give you a little bit more time to digest the information that we're going to go through today and do the homework. So I know that'll probably help some people. Okay. Because this information is not hard, but it does take a little bit of a learning curve, and so yeah. So the homework group 3 is going to be. I'll send an update out. I had meant to do that, and I need to update one of the problems because I accidentally repeated it. But essentially, the homework that'll be due for the test will be so the homework due on Wednesday will be through chapter 6. Okay. So that was. So is there any other questions? Okay, so feel free to post your questions while I talk. I'll try to keep an eye on the chat so that I can pause and address them. Today's lecture is pretty important. It's the summary of kind of what we've been building up to. I have brought out some of the examples from the text that are in the text that we can go through. The examples in this book are particularly well selected, and I'm closely following the book for this chapter because it's one of the best treatments of fatigue that's available. And I think between the book, this lecture, and the lecture videos that you have from Norton, that if you put all those things together, you'll have plenty of information to understand what we're doing. So in light of that, I just have a suggestion. I know many students don't read their book, but I'm going to remind you to read your book. Your book is good, so read it. I have the assigned readings that you're supposed to have read before we have class so that you can bring questions. I know that life doesn't always afford you the time that you want to do everything. But just a reminder that the book is good, and he's done a great job of presenting the information. I'm going to try to make it a little bit easier for us to go through for you. But it's everybody's going to be kind of at a different level, so it's really important that you jump into the book and kind of are ready for these lectures. All right. So we are continuing the discussion from Chapter 6 about fatigue. And for fatigue, the axial stress is tensile stress is a big deal. And because it's such a big deal, there's methods that we can use to introduce residual compressive stresses. Now, when we talk about residual stresses, many of the manufacturing processes, such as forming, heat treatment, etc., will result in residual stresses in an unloaded part. So what that means is that if you were to zoom in on a little tiny stress element, which we represent as a little cube, but we know it's actually a point in space inside the material, all we're saying is that material at that point in space in that material can have a three-dimensional state of stress. In fact, every point in the material probably has some non-zero residual stress, even if that stress is really, really small. When we do different manufacturing methods, that various points in the material can experience different states of stress. Okay, and the way that we make metal with hot rolling or cold rolling or forming or etc. often results in residual stress. Metals like steels are often annealed to relieve some of that stress. They basically heat it up and let the stresses go away. But just keep in mind that residual stresses are present in a material just because of just how the way the raw stock is made. We know that fatigue is a tensile stress phenomenon because it's related to cracks, and if you're pulling the cracks apart, in general, it's bad. And so if we can, introducing a compressive stress that's a residual compressive stress in the material can improve the fatigue life considerably. We can create compressive residual stresses by thermal treatments and surface treatments and mechanical pre-stressing. We'll talk about those. These compressive stresses can be your best friend for fatigue life. We'll talk more about that. The stress has to be balanced, though. So if you have a compressive stress at the surface, that means you're going to have a tensile stress somewhere inside the surface. And I'll show you some cross sections of that. The cracks at the surface are a primary concern. So compressive stress is desirable to kind of close those cracks and improve the life. But if you have too much internal tensile stress, you can also create a problem. And so a balance has to be made. The point of this class is for machine design, not necessarily how to design a process to introduce residual stresses, but you should be aware of their benefit for fatigue. When we talk about high-strength materials, those are the materials that benefit the most. They're usually more brittle as well. Materials that have a low yield strength of less than 80 kpsi show little long-term benefit of residual stress. And we're talking specifically about fatigue. The way that we introduce residual stresses are through thermal treatments, such as through hardening and case hardening. Through hardening is not really good for fatigue. That's where you harden the entire cross-section of the material by heating, quenching, and tempering to modify the strength and toughness. This is good for seat belts, belt buckles, hand tools, springs, axles, and such, nuts and bolts, nails, but not so good for fatigue. Case hardening, on the other hand, which is used for a lot of dynamic mechanical components like gears, camshaft, universal joints, etc., that are subjected to cyclical loads. You have construction cranes there. That's because obviously when you have a long cantilevered arm, it will be subjected to bending stresses, cyclical bending stresses, as it picks up and lowers stuff. And so another way we can introduce residual stress is through the surface treatments, and those are shot peening, laser peening, cold forming, and we can actually also mechanically pre-stress a component. We'll talk about those. All right. So we mentioned through hardening is not really good for fatigue, and it does improve the ultimate tensile strength for steels because the hardness in a steel can be related to its ultimate tensile strength, and we saw that materials with higher ultimate tensile strengths can have higher fatigue life, but these can also create residual tensile stresses, which is not good for fatigue, and we would not call out necessarily typically a through hardening process or buy a material that's through hardened and then put it in a fatigue application. So you as the designer will have to do more work than we cover in this class by looking at like the machinery handbook or Mark's handbook, or just researching the specific materials that you're thinking about using to make sure that you make a good choice with this in mind. Another thermal treatment is case hardening, and that's where we create the residual compressive stresses through carburizing, nitriding, flame, or induction hardening. And that's where either we, in carburizing, heat it up in a carbon-rich environment, and nitriding, same thing, we heat it up, and the nitrided material goes into the outer surfaces and makes it really hard. We can also use flame or induction hardening, where we heat up the outside of the metal to change its crystalline structure and then quench it. So we get a martensitic steel, and that is it's a larger crystal lattice, and so it causes it to become, the volume of the outside surface becomes slightly larger through the introduction of the carbon or the other elements. And what that causes is you have to have balances of forces, and so the forces inside pull the material together in a compressive nature. These graphs down here show a carburized and a nitrided material, and you can see the difference. So if you have a nitrided material, and you look at the compressive stresses here, this would be 0, so that means 0 is 0 stress, and these are negative stress values. And so you can see as you go down through a material, if you start at the surface and you go down here, you get pretty high compressive stresses, and actually they increase beneath the surface to a point, and then they come down and they go back to 0. And if you look at the carburized steel, you see that it has negative compressive stress here, and it goes down, maintains its compressive stress, and this is through the material, and this is in inches. So to a 25 thou, you get, or about 20 thou, you get your peak compressive stress underneath the surface. If you zoom out, this is what the overall material looks like here, and you can see that for a carburized element, you get these nice, beautiful compressive stresses at the surface. You have to have a balanced tensile stress in the inside surface to balance that out. And if you go to the other surface, you have compressive stresses. Okay, and down here you can see that these are negative values. That means compression, and over here, this means tension. Okay, and so it's a common way of us improving the fatigue life through case hardening. Another thing that's done in many applications, lots of aerospace, is shot peening. And shot peening is essentially where you shoot small pieces of material such as glass, steel, cast iron, even walnut shells at the surface, causing the surface to deform. And so the surface, if you zoom in, depending on the size of the shot, you'll see a dimpled surface. what's happening is it's causing the surface to deform and stretch out, and then the internal material balances that force and causes it to pull together, so you get an external compressive stress. If you look at the shot peened surface here versus a nitrided surface, you can actually get even more compressive stresses, and that's widely used on gears, camshafts, U-joints, and other things. Okay. Another way of us getting residual stresses is by cold forming, and the principle is very similar to shot peening, and that's where you deform the outside surface of a component, and by deforming it, you cause it to yield and then move. And when you stop the process, the internal forces cause the compressive stress to form on the outside of that surface. Cold forming is done by squeezing, like through an extrusion or rollers, bending, shearing, drawing. It leaves the metal harder through strain hardening on the outer surface, and that's how we get those residual compressive stresses. It's also used in holes, where holes would be drilled, laser cut, or however, and then you'd go in with a tool to make the hole slightly larger to the final dimension, and that's a cold working or cold forming process, which just mechanically stretches that material out to create that residual stress at that surface. This is not really a fatigue application, but it does show you the process of cold working, taking a blank of component and then turning it into a final piece. Cold forming is particularly useful where you have fillets, grooves, or other stress risers for engineered features such as O-rings, gaskets, and things like that are necessary part of your design. You can use cold forming to improve the fatigue life for those features. Another thing that we can do for improving fatigue life is mechanical pre-stressing, and this is an example of a leaf spring. And the part is overloaded in its service direction. So if you take a look at this picture, this is the leaf spring as it's formed and heat treated. This is the nominal geometry, and that nominal geometry is shown in the dashed line here in these figures. Okay, and so the first thing you do is stretch it above the yield strength. Okay, so this is the yield strength in tension, and this is the yield strength in compression. This would be an even material because you see we have equal distances for tension and compression. And so if we slightly yield it and then release it, then we can see here that the state of stress, because we yielded it, actually produces a compressive stress on this side of the surface and a tensile stress on this surface. Then what is done is we can shot peen it. Okay, so when we shot peen it, we increase the residual compressive stress on that surface. Okay, and then we still have residual compressive stress in the surface, and we have a smaller tensile stress in this direction, so that when it's loaded in its working load condition, okay, instead of having this case up here where we have this large tensile stress, what we actually have is this notch down here. Okay, so you see this little tiny gray sliver. So what we did is we actually were able to significantly reduce that tensile stress on that surface. Okay, we also slightly reduced the compressive stress, but the benefit outweighs the cost there. So there's a question: which is cold rolling and cold forming the same? So rolling is a forming process. So yes. All right. So are there any questions? Any questions about surface treatments? Okay. All right. So now we're going to talk about putting everything together that we've discussed so far. And I would ask that you try to follow along, pay attention, ask questions, because if you do, I think it'll make it a lot easier if you go through the material, or if I give you a problem that requires design for exam 2. What I'm about to talk to you about can make your life a little bit easier. Okay. So there's 4 categories of loading. We can have uniaxial stress, and that's where we have a mean stress. Uniaxial stress, which is where we just have stress on one principal axis, and 0 mean stress. In this category is uniaxial fully reversed. Okay, and so this would be sort of like our RR Moore bending test machine. If we have a non-zero mean stress, then we call this, and if it's a uniaxial, if we also have uniaxial and non-zero mean stress, this is a category 2 loading condition. If we have multiaxial stress, where our mean stress is 0, this is category 3, and multiaxial stress with fluctuating stresses is category 4. And we're going to go through each one of these and show a couple of examples. Okay. So I know this has a lot of information on it, but I still want to talk you through this. This is the simplest case for fully reversed stress, 0 mean, that's category 1. And so how do we put everything that we've seen so far together and actually do design? Well, the first step is to determine the number of cycles that you want for its expected life. So you're going to have to think about, how is this going to be applied? What loads do I expect? What are the amplitudes of the loads, and etc. Note that if you have a rotating shaft and you have a static load that in a single direction, then that actually causes an alternating bending stress because of the bending stress, the way that we get compression on the top and tension on the bottom surface away from the load. And then to design, we actually have to pick a geometry. And so this is where tools like EES come into play, where you can actually kind of set up all your equations and you can play around with your part geometries and calculate everything out to see if your design works. Obviously, Excel will work as well. And then once we select a geometry for that loading condition, then we can take a look at our stress concentration factors. Okay, which is KT. It's a theoretical stress concentration. That was from chapter 4, or KTS if it's in shear. And that is the notches in your part's geometry. And obviously, we want to minimize these stress concentrations by avoiding abrupt changes in geometry. So then we want to choose a material. And then we need to find out, well, what's its ultimate tensile strength, what's its yield strength, what's its endurance limit, if it's a material that has a knee, or if it's fatigue life, if it doesn't have a knee. And then we can find Q. We'll talk about what Q is in detail in just a minute. That's the notch sensitivity, sort of a measure of how sensitive a material is to a stress concentration. And then we will get estimates for the fatigue life that we can use, and that's what we'll discuss here. We have to modify the stress concentration factors from chapter 4 for fatigue concentration factors. And We do that by knowledge of that material's notch sensitivity. Okay, and we'll talk through that. Then, after we kind of have an understanding of the fatigue life and such, then we can calculate our stresses. What we care about for fully reversed stress, because we have a zero mean, is the amplitude of the alternating stress. And we just need to calculate it where the stress is the max at the critical locations in the parts. We calculate those stresses based upon our statics analysis from previous classes, and then we modify those with the stress concentration and fatigue stress concentration factors. Okay, so after we get the stresses, then we need to calculate the principal stress amplitudes, and those include the stress concentrations. Then we calculate the von Mises effective stress for each element, and then we go through and we add the fatigue strength modification factors based upon the factors that we discussed last time. And the note here is that when we have the load factors, if we have a pure torsion, what we do is we calculate the von Mises effective stress, and we can keep that load factor set to 1. So if you'll remember, the load factor only had bending and axial loads. So if we have torsional loads, we calculate the von Mises effective stress, and we use the load factor for 1. So then we calculate the corrected fatigue strength at the requisite life. Okay, so we started with how long do we want this to last. Okay, we went through these processes, we calculated the actual stresses, and then based upon those stresses, we can calculate the fatigue life, the corrected fatigue life with those correction factors, or the endurance limit. And then we can actually create an SN diagram based upon the relationships that we talked about in the last lecture. And then we can compare the alternating von Mises stress for that location at that number of cycles. And then finally, we can see how we're going to do with that effective stress and this fatigue life, and calculate the number of cycles that that material can survive. All right. So the problem with this is it's a chicken and egg problem, right? So we have to make some decisions about part geometry in order to calculate the stresses. But once we calculate all the stresses, we may find that for that material that we won't be able to do it. So what people usually do, they'll design. If the design doesn't meet the criteria of the problem, then we'll go back and modify the geometry. Okay, so we modify the geometry so that we can, reduce the stress, which it usually involves making that part a little bit larger, so that those loads are picked up by more material. Okay, so often you design against the load, and that means that what you do is you end up going back to the geometry and then going through this process again. If you have this written up in an Excel spreadsheet or in EES, though, you can play around with those factors and quickly see what all these are. So I would highly suggest you get some software support for this, just so you can get see things a little bit easier. All right, so this is for category 1. Okay, the approach is going to be pretty much the same, but we have to discuss some other things for other cases. All right, so this is a design problem, and in this problem, we have a bracket here, and it's going to be 1/2 of a machine, and it's going to have the same bracket on the other side. Okay, and it's going to support a feed roll assembly at the end of each of these brackets, and the load that one of the brackets experiences 1,000 pounds, or actually, so 500 pounds each, 1,000 loads between the two. And the question is, design a cantilever bracket to support fully reversed bending. Okay, when you see fully reversed, that means the mean stress is 0, and we only have an a alternating stress. We want it to last for 10 to the 9 cycles. So when you see 10 to the 9, okay, we have the fatigue charts for aluminum for 5 times 10 to the 8. So when I see that, I think, okay, that points me in the direction of steel because it has to last for a really long time. So I probably need to design against the endurance limit. We also have a deflection requirement here of 10,000ths of an inch. So this is a fully reversed case. Here we have a max of 500, minimum of minus 500. And we have this rectangular cross section. Okay, so there's some assumptions that are made that it can't be clamped, that it can be clamped between rigid plates bolted at its root, that the normal load that's applied to the tip is through a small hole, but that the hole is far enough towards the end of the beam where the bending moment is pretty much 0, so that we don't have significant stress concentrations from that hole. And since they say they only would like, I think, 10 of these, how many do they want? Let's see here. So this is a low quantity. It says it's somewhere. Let's see here. If we were in class, you guys could probably point it out to me. But given that we have a 10 or 20 second lag, all right, so somewhere I thought it said we only needed a handful. So there's a small quantity, and so because there's a small quantity, the machining of a stock readily available shapes from a mill are preferred. All right, so this is pretty much how we would see a design problem in practice, and that is where we're kind of given enough information about the problem to get started, but we're not necessarily given all the information about the geometries and stuff like that. So as such, it is a design problem. We really only have performance requirements, and we know how long it needs to last, and we have some constraints in terms of the size. It can't be greater than 6 inches. Oh, this is where it says only 10 parts are required. Okay, so you have to make some basic assumptions. So, all right, so what we do is we're following the process that we walked through. We pick a tentative design. This is a very good discussion. It says, to make life easier, we can choose a rectangular cross-section that allows us to have the roll to slide over it and automatically retain it. And it's a readily square channel is readily available from the steel yard. It's simple. You can actually machine the surface, get a slightly larger one, and get a machined surface so that you get the tolerances, because you may or may not get the tolerances directly from the mill. We have sharp corners here. Right here, we're going to have a stress concentration. It's a problem for fretting. Fretting is a type of surface wear under high load, and we can have fretting fatigue. We'll talk about that more when we talk about surfaces. You don't really need to know so much about fretting fatigue as you do need to recognize that if we have a sharp transition to like this, where we go from this geometry to this geometry, that we have a sharp change in the geometry, and this is undesirable. And so in order to reduce that, we can pick a different shape, get an oversized part, machine it down so we have smaller stress concentrations. Okay, and we'll talk more about surface failure later. So we can machine it, and then we can calculate the stress. When we calculate the stress over here, then we got to go back to the stress concentration figures from chapter 4 for the static case and calculate using that CATI that we'd get from the charts or from the tables associated with the charts and interpolating between them. All right, we calculate our R over D and D over D ratio. That would be this radius here and this D over D. Find the appropriate graph, plug in the dimensions, and we can pick out our stress concentration. In general, you'd like to keep it lower. In this case, the design is to keep it under about 1.5. All right, so now we get to the place again where it's the chicken and an egg. We have to pick some dimensions. All right, and so go ahead and pick some dimensions. They're labeled here. That'll allow us to calculate the stresses, and we have to pick a material. Okay, so if we want infinite life, we want a cheaper material, we can pick a low carbon steel, and that's assuming that, you know, the environmental conditions permit. Maybe this is in an air-conditioned space or at least 5 miles from the ocean. And we'll say, so, well, since it's in a controlled space, we can pick steel. It's okay. The deflection is a concern. Here we say it can't deflect more than 10 thousandths of an inch. And so in that case, we want to have a material that has a large Young's modulus, so that we have a steep slope in the stress strain curve. So that means that if we have an amplitude of stress, it results in less strain if we have a steeper Young's modulus. And so in this case, 1040 was chosen. It's really readily available and has the ultimate tensile strength of 80,000 psi. And so that gives us a lot of information. We're making decisions about geometry and material before we even calculate the loads and fatigue life, but we have to have that information first. And so this is where design just is about, you know, making good decisions, learning about all the material options, and then going through the process. In order for us to move forward, we have to get the actual loads. And those loads are found from our static analysis. We find the reactions. In this case, we have, an end load force here. It has to be balanced by a reaction force here, but it also causes a bending moment because of this moment arm from 0 to A. We can plug those numbers in. We can calculate our bending moment. We can calculate our reaction forces. We can calculate our moment of inertia, our distance to the outside of the beam. That's the C and this MC over I. Once we have the moment, distance, moment of inertia, we can calculate our nominal alternating bending stress. Okay, and that's about 27 kpsi. All right, so we still haven't solved the problem yet, and so we have to go through the rest of the process. We get our geometry ratios so we can pick our stress concentration factors. We can use the equation form, or we can pick off the chart. In this case, this is a figure from 436 in your book. Stress concentrations are also showed in Appendix C for different materials. And using the geometry that we picked, we can find a stress concentration of about 1.29, which is below the 1.5 that we said we wanted. Now, as we saw last time, we can calculate the stress concentration, the notch sensitivity. And that notch sensitivity we can either get from the tables, or we can get from the Neuber equation. Okay, and in this case, from the table, we see we have an ultimate tensile strength of 80 kpsi, and we plug those parameters in, we get the square root of A. This is not the same. This is different than the crack length. We're talking about the notch sensitivity equation calculated from the Neuber constant. Okay, so if we do that, we can calculate a Q, and then we have to calculate our dynamic fatigue value using Q and the static stress concentration to get our fatigue concentration factor. So we use the equations that we talked about last time, and then we take our nominal stress, which was 26,000, and we multiply it by our corrected fatigue factor here. Okay, and we get 33,343. So then we can calculate our principal stresses here using the equations for the principal stresses. And we find that in this case, which we expected, we had the uniaxial loading, we will get the same value. But this is the right process, and these are the right equations. Okay, so even though we know that we're going to get the same value out of the equivalent stress, because that is the stress that's applied, in the uniaxial case, it's still the process that we would go through to calculate the effective von Mises stress. Okay. All right. So now we can go into the fatigue estimates. Now, we said that if we don't have fatigue data for that particular material, we can estimate what it is based upon 0.5 times the ultimate tensile strength. If we do that, we get an uncorrected endurance limit for steel of 40,000 psi. In this case, since we don't have the round circular cross section, we have a little bit different case. We can take the A95 area that we discussed in the last lecture and calculate that to get an equivalent diameter, and we can plug that equivalent diameter by finding the right equation of the three equations. Plug that in, and we can get our size factor. Okay, so that's the first of the five factors for correcting for this fatigue life. This is the uncorrected. It has a little prime there. It's probably hard to see on your screen, but that's what we have to do. So then we can go ahead and get the rest of the load factors. In this case, we want to have 99.9% reliability. That gives us a reliability factor of 0.73. We say it's in room temperature, which gives us a temperature factor of 1. We look up the chart for the machined surface, or we use the equations. And then we can get that the surface factor for machine surface for this ultimate tensile strength is 0.845, and then we have the load factor for bending. Okay, so don't be afraid of all of these equations. The process is the same. Okay, we have to start, we have to calculate the things that we don't know, and then we have to make sure that it won't break. Okay, so now that we have the correction factors, we can calculate the corrected endurance limit for that material by taking those factors, multiplying them by the nominal uncorrected endurance limit, and we get about 29% of the predicted endurance limit for a polished specimen from a Moore test. Okay. So once we are all the way down here, and now we have an estimate for the endurance limit for the fatigue life, well, then we can look and figure out, well, what is our safety factor? Okay. And what is the beam deflection, and did we get where we needed to be? So our safety factor is going to be the fatigue, the corrected fatigue stress at N. In this case, it's 10 to the 9. So we want to go all the way to the endurance limit over the von Mises effective stress, and we find that it's 0.69. So okay, we're not going to be there. The material is going to fail. We can use the equations for those loading conditions from example 4-5 or from the back of the book. For this beam loading, we find that the deflection is related to this, okay, equation here for the deflection, and the max deflection is going to be at the tip of the beam. So we can plug in the tip of the beam, plug in the parameters, and find that the deflection here is 26 thousandths. Okay, so this design failed both in the safety factor because it's less than 1 and in the deflection. So what do? What we do then is we have to go back to the design and modify the geometry. Okay, so this is what was done for this example, and the dimensions were increased from these nominal dimensions in the original design over to these. Okay, most of this stuff down here is all the same. Okay, it's just these dimensions here in red that changed. Okay, so by increasing the size of the material, what we did is we dropped the equivalent stress for the von Mises. Equivalent stress, we have then a safety factor. We have about the same endurance limit here, but the safety factor now is 2.5 because the effective stress dropped so much because we changed that cross-sectional geometry. So what I'll do now is see if we have any questions, and just pause there for a second. So I know that people who are watching this later might not appreciate the long pause, but I want to make sure that we can address any questions. All right, so that is for category 1 loading. Okay, that's what we just did. Okay, we just did this category 1 loading, uniaxial stress, okay, and 0 mean stress. Okay, we saw last time that if we have a mean stress, okay, this is the fatigue ratio, this is alternating stress over the fatigue strength. This is the mean stress over the ultimate tensile strength, and we found that this is the failure line for steels for 10 to the 8 to 10 to the second, 10 to the 7 to 10 to the 8 cycles. We have a Goodman line, which goes from the alternating stress over the fatigue strength, which is at 1. Obviously, you have failure if you exceed that fatigue strength with alternating stress in the presence of 0 mean stress. And then as you move up here and you increase the mean stress, then the fatigue life drops dramatically. Okay, we've seen this for steel. We've seen it for aluminum, and we've seen it in a different way of looking at the data here, where we plot it in terms of tension and compression. When we have 0 mean stress, here, this is the nominal case. When we introduce a tensile stress, we get reduced life. If we introduce a compressive stress, we get increased life. And we've seen it down here in terms of the alternating stress and the number of cycles to failure. With 0 mean stress, this is our nominal SN curve. When we have compression, we get higher, longer life, and we have tension, we get lower life. All right. So what we can do is we can take a look at the presence of a mean stress and an alternating stress, and instead of expressing it like we did here, where we have it normalized to the fatigue strength, the alternating stress normalized to the fatigue strength, or the mean stress normalized to the ultimate tensile strength, we can look at this diagram here, which has the modified Goodman line and Soderberg line and Gerber line and our yield line. And we can, these are different theories of failure for the presence of a mean stress. And what we will use is we will use the modified Goodman line, which we saw is underneath most of the data. And we'll come down here and we'll follow this line to the yield stress. And we'll call that the augmented modified Goodman line. And these lines are plotted. If our y-axis is the alternating stress, sigma A, we know the endurance limit, we can calculate these lines using the mean stress over the ultimate stress squared as we vary the mean stress from 0 all the way to the yield or ultimate stress. And that's how we can get these lines. And we'll use those lines to get us an estimate of our safety factors for fatigue in the presence of mean stress. Okay, if we look at this effect of mean stress, here we have our nominal SN curve, okay, but then as we add a mean stress here, then those curves die down. If we project those lines onto a 2D plane, here we have our nominal SN curve, and then as we increase the mean stress, that SN curve goes and drops all the way down to 0. Okay, so the presence of a mean stress greatly reduces the life of the component. We can also see over here, this is called a constant life diagram, and this is where we plot the alternating stress versus the mean stress, and we see that as the number of cycles goes from 10 to 10 to the 8, that we actually get reduced life according to however many cycles. So this is all presenting the same information in different ways, and it's to highlight the effect of both a alternating stress in the presence of a mean stress, and this is the category 2. Okay. All right, so we'll go back up and we'll look at our categories. Okay, so we're talking about when we have category 2, we have uniaxial stress, but we have a mean stress. Okay, so this is category 2. Okay, and so what we can do is use this augmented modified Goodman diagram. So we take the Goodman diagram and we will augment it by drawing this line down to the yield strength. So even though you can have a material that will survive out here, if you're out here, you're past the yield strength, and so you're going to get a dimensional change in your material. So it's nice to know where you are on this graph so that you don't yield the material. Okay. So line BC, this is compressive failure. Line CF here, this is the fatigue failure with tensile mean stress. Line GE is yielding in tension. Okay, and we need these lines to determine our safety factor, because what we're going to do is based upon the endurance limit or fatigue limit for a material, we'll want to be down here. And our safety factor is going to be calculated by how far away we are from this line or how far away we are from this line. All right. And these are the equations for those respective lines. So let's see if we have any questions. All right. And note that these are the sigma primes. Okay, so these have to be corrected for the stress concentration factors when we use them. Okay. All right, so how do we use the Goodman diagram when we have a stress concentration factor? Okay, well, if the material is brittle, then we don't make any changes to the dynamic stress concentration. We just use our nominal relationship that we saw before with the Neuer constant or stress, the notch, the fatigue Q, which is the notch sensitivity, and we use that to find KF, and we can multiply that by our nominal load to find our sigma A prime. And note that these plots are plotted in prime. We have a situation, though, where if a material is ductile, then some yielding may be okay. Okay? And in order to account for this, for ductile materials only, we can use the dynamic fatigue equations before for sigma A, just like it's shown. But if we have a mean stress in the material, then how do we account for that? Okay, and that's how. In other words, it's saying is like, well, we know how to calculate the alternating stress with the dynamic fatigue factor and the static stress concentration. How do we do that for the mean stress when we have a mean stress? Well, we have three cases, and that is if the nominal mean stress is less than the yield stress, then we just use the same dynamic stress factor. Okay. If the stress is greater than the yield stress, then we actually get a lower value for the dynamic fatigue limit because it'll stretch and then stay there. If we have reversed yielding, where the material will stretch in one direction or plastically yield in one direction and then plastically yield in the other direction, we actually set that to 0. Okay. So for this approach, what we do is we assume elastically perfectly plastic material, which says you go up to some load. Once you get to that load, you have perfectly plastic deformation. This here is the stress zones from a stress stress due to the stress riser of the hole. And if we have this nominal stress that exceeds the yield stress, then we may have some plastic deformation in this zone. Okay, so how do we deal with that? Well, what we do is we have those three cases. In the first case, we have no yielding, so you just go up the stress strain diagram and go back down. And in that case, we just use the nominal fatigue stress and concentration factor. If we have some yielding, we go up to some value, and then we remove the load, and then we'll just go up and down that value because we've already yielded it. As long as we don't exceed the max stress, it's okay, but we still have to account for that stress concentration, and we can do that with this equation. If we have reverse yielding where we stretch the material and then remove the load in the other direction, we essentially have a net zero yielding because it's fully reversed yielding. In that case, we have a KFM that's equal to 0. Okay, this is the KFM fatigue factor where we would modify the mean stress. Okay, so we'd multiply our mean stress by KFM. We find that KFM is the same as the fatigue stress riser that we used before, all the way up into the yield strength. If we exceed that yield strength with the stress that's applied, then we use this equation here. That equation maps out this space. And if it's fully reversed, then we go and we make the KFM equal to 0. Okay, so that's how we account for stress concentrations in ductile materials when we're trying to find our fatigue safety factors and build the modified Goodman diagram. Okay, so the safety factor then that we choose is going to depend on how the component will be loaded in service. So we have 4 cases. Okay, case 1 is where we have a alternating stress. That alternating stress doesn't change, but the mean stress may change. Well, in that case, if we have this point of operation that we designed to, then our safety factor is going to be this distance over that distance. Okay, and in the case 2, if we have a mean stress that's applied to a material, but we have an alternating stress that may vary, then this is the way that it will fail. It'll fail by if the alternating stress hits this value, and so then our safety factor is this length over this length, and we'll get equations and expressions for that. In the case where we have the amplitude of the alternating stress and the amplitude of the mean stress that can vary, but they vary as a ratio of one another, then we'll go up this line, because this is our y value is the alternating stress, our x value is the mean stress, and if they go up together, then they'll have the same slope. And then our safety factor is this line divided by that line. If, on the other hand, we have the case where the amplitude of the alternating stress and the amplitude of the mean stress can vary independently, we have to account for that. And the way that we do that is we find the shortest distance from our operating point. This would be our nominal case right here that we're going to design against. And then we want to get our safety factor, and we would find the closest value to that point there. Okay, if we map that down to S prime, then we'll get this length here of that line, and that'll be the safety factor will be this line over that line. And you can actually calculate all 4 safety factors just by plugging them in. You plug in your state of stress, and you can see, what's the most limiting safety factor, and you can choose that. If you're within your design constraints, then you don't have to worry about the other cases because you already considered all of them. So, all right, so this is case 1. We already talked about it. The mean stress can increase. This is the equation for that line, and this is the safety factor. Okay, so then you can just find those points, plug those values in, and get your safety factor. For case 2, if the alternating stress can increase, then you're going to fail. This will be your point of failure here, because that's the line you'll go to where you'll experience failure. These are the equations for that, and you can find your safety factor from those relative lengths of those lines using these equations here. For case number 3, if we have where the amplitude of the alternating stress and the amplitude of the mean stress vary together, then you'll find this distance. You can create 2 equations, 2 unknowns, and then you can solve for them, and you can get a sense of the stress here at R, and then a safety factor based upon those relative lines. Okay. Case 4, where we can vary the amplitude, where the amplitude of the alternating stress and the amplitude of the mean stress can vary. Then we find that closest point of failure, map it down, and then calculate the safety factor like that. And that's the ratio of those lengths here. We can calculate those lengths using these equations. By no means do I expect you to memorize these equations, but by all means, I expect you to be able to look them up and use the appropriate case. Okay, so what do we do for fluctuating stress? Okay, this is a design for fluctuating stress. Well, it's very similar to the case of the fully reversed stress. We just now have to consider the effect of that mean stress. So first step's the same. We get the number of cycles. We find the amplitude of the alternating and the mean and peak loads. We calculate the mean stress and the amplitude of the stress. We create a preliminary geometry that we think will satisfy that design. Based upon that geometry, we're going to have if we have any stress concentration factors, we're going to find our static stress concentration factors. We're going to convert those to the fatigue concentration factors using the material's notch sensitivity. Then we have to calculate the nominal stress amplitudes of the alternating stress at critical load points. And then we'll have to modify those with the fatigue stress concentration factors if we need to. And then for the mean stress, we'll have to modify that with the fatigue factor for the mean stress, as we've just discussed. Once we have those stresses, we can plug them into the von Mises. Notice the order, right? We have to calculate, we have to get our service life, calculate the applied loads, pick a geometry, find our stress concentrations, find our dynamic fatigue concentrations, and then calculate our nominal stresses, and then we calculate the von Mises stress. If you just go directly from, the applied loads to the von Mises stress, you're going to end up with the wrong values. Okay, so we calculate the principal stresses on stress amplitudes for the critical locations. We then pick a material. From the material, we get our ultimate tensile strength. From there, and the yield strength, we can get our endurance limit or fatigue life if it's aluminum. And we'll use the notch sensitivity data or the information that's available to us to then begin to do the design. We then we then determine our load factors, and then we calculate the corrected fatigue strength or endurance limit. We create a modified Goodman-Diagram, and then we use the corrected fatigue strength. If you look here, this is the corrected fatigue strength. Okay, we use the corrected fatigue strength with the load factors, and then we can plot the mean and alternating stresses on the Goodman diagram and calculate the safety factor from one of the 4 relationships. Okay. So it's often that when you do this, you have a design that fails and you have to repeat and go back to step 3, okay, where you have to play around with the geometry. Okay, so that's a common practice. Usually we don't have control of the loads, and so we have to deal with that. I'm going to go back here real quick. This is how we calculate the alternating and mean stresses. Sorry I didn't mention that when we were on the slide. Okay, so we calculate these alternating and mean stresses from the mean stresses that we experience. Okay, so if a stress is applied that's a mean stress, then we have a mean value, and we use the mean stress in the X and Y and Z. This is for the triaxial state of stress if we have this. We'll talk a little bit more about that later. Or for the case where we have biaxial stress, then we will use this to calculate the alternating and mean stresses from the alternating and mean values of stress. And all that is just simply we calculate the alternating value of stress, right, as defined by this graph here. Okay, so when we have a component that's loaded, if we have a mean component, that's our mean stress, okay, and then we can find the stress on the X and Y faces using Moore's circle, and we have the alternating stress, which is the amplitude here of that stress, okay. So the amplitude of the alternating stress goes here on those faces. The magnitude of the mean stress on those faces will go here into the mean stress equation. And in the biaxial case, we have this here, okay? So this is what changed from the fully reversed stress. We have this component to deal with. Okay, we calculate it, but we separate the stresses out, the ones that are alternating and the ones that have a, non-zero mean value. Okay. This is the process. If you follow this process, then you're going to be able to go through the design process. Obviously, there's a lot of new grammar, and so it will take you a little bit of time to digest this information. And so I encourage you to, read through the book, and if you something that's confusing or whatever, just maybe pause and go back through the video. All right. So this is the same example, but in this case now we have, or it's a similar example, but in this case we have a load that varies from 200 to 2,200 pounds. Okay, so we have twice the load and 200 pounds of a mean stress. Okay. In this case, we have this load here. Okay, that's a non-zero mean. So the mean is the average of the stress. And we have sigma min, sigma max. So this is the amplitude. Okay, so this is sigma m, and this is sigma a for this case. We want it to last for 10 to the 9 cycles. Okay, and it can't deflect more than 20 thousandths. This time we're told that it's at a slightly elevated temperature. We're still limited to only 6 inch. We only need 10 parts. We assume that it can be clamped. We already learned that we want to do a stress relief fillet. And the load is applied to the tip, and we can ignore the stress concentration because the bending moment there is effectively 0. Okay, so again, typical design problem. We can take the geometry here, calculate the static stress concentration. For infinite life, we use carbon steel, choose 1040 again, same 80 kpsi, yield strength of 60. And then in this case, we have to calculate our different stresses. Okay, these are the dimensions here where we pick the size of the beam. Again, we picked a square cross section, but obviously this might change depending on how well we do the first time around. So I know we're almost at the end of the class, so I'll finish this example and we'll end the lecture. So based upon the force information given, we can find our mean stress as the average of the max and min stress to be 600 pounds, and our alternating stress to be the difference between the max and min stress over 2 at 500 pounds. Okay, so we solve the statics problem. We find the reaction is 500 pounds, and for the alternating stress, for the mean stress, reaction is 600 pounds. And that the max value is 1,100 pounds. So then we can calculate a alternating bending moment, and then a mean bending moment and a max bending moment. Okay, we need the max bending moment so we can look at the deflection. We can calculate the moment of inertia from the cross section, the distance to the neutral, from the neutral axis to the outside surface of the part. Calculate our nominal alternating stress, our nominal mean stress from the nominal alternating and mean moments from our forces to be 7,500 psi and 9,000 psi. We can get our static stress concentration factor from the material in the book and the charts. Then we can calculate the dynamic stress concentration factor from the notch sensitivity using the Neuber constant and the radius of the notch. We can plug that into the equation and calculate the fatigue. Then we have to find out for the mean stress, okay, if it's less than the yield stress, which we're given in the problem for that material, then we just choose we say that the stress concentration for the mean stress is just the nominal dynamic fatigue stress concentration factor. Okay, so then we can calculate that max stress here, and it's slightly larger than the nominal value. We just take the dynamic stress value, multiply it by the bending stress, and then calculate that. We modify the nominal stress by the fatigue stress concentration factor for the alternating stress to get that point in the Goodman-Diagram. And then we do the same thing for the mean stress to get that other point, to get the XY coordinates in the Goodman-Diagram. And then we go and calculate our effective amplitude of our alternating stresses. Okay, and in this case, they work out to be the same, which we expect because of the way that it's loaded. But if it were the case where we had some shear stress or whatever, we'd have to account for that and would change the values here. So now we got to get into the fatigue design. Okay, fatigue design using material properties of the ultimate tensile strength, we can estimate to be half. We can calculate the A95 area to get our size factor. We can get our load factor, surface factor, temperature factor, which in this case it's slightly lower. Actually, it's still 1 because we're within the temperature range. I think it goes up to 450 degrees. And then we have our reliability factor of 99.9. So then we have our corrected endurance limit of 21,000 psi. Okay, so now that we have the value for the endurance limit, we have the value for the effective alternating stress calculated from the von Mises equations, the effective mean stress calculated from the von Mises equations, the ultimate tensile strength, which is the material property. We can plug that in, and for case 3, in this case, we have an alternating and mean components that have a constant ratio. Then we can find that our safety factor is 1.9, and that our deflection is 12 thou. Okay, so that's good. It satisfies the requirements if we are okay with a safety factor of 1.9. Okay, if we increase the cross-sectional area of the materials and go slightly higher, okay, we go from 1 of the inner diameter to 1.2. Then we can drop the stresses down, here, and here, and we can improve our safety factor a little bit. Okay, so we can go ahead and just use the equations that we have, though, and calculate all the safety factors for all different cases and take the minimum safety factor as a more conservative approach. All right, so I know that this lecture has run 5 minutes over, so we are going to go ahead and stop here, and I'll see if there's any questions. All right, so we'll go ahead and stop here. And remember that we have office hours with the TA tomorrow. Oh, I'm sorry, on Friday. So if I encourage you to read this book, this is probably the most challenging material of the book, but just because there's so much new terminology and, sigma A versus sigma A prime and SE versus SE prime. You can't just digest it in a couple of minutes. You really have to sit with the material. I've tried to make it as easy as possible. I know that we kind of went through these slides pretty quickly. This is follows the same pattern in your book. This is a very good treatment of the subject. So it's such an important part of your design experience. Fatigue accounts for 90% of the failures. So I highly encourage you to go through the books, make sure you understand the examples. For the test, I will certainly give you a problem where you're going to have to go through this design process, but I will give you enough time to solve it. But you won't have enough time to probably learn everything and then solve it. So please prioritize this subject. It's a very important part of your mechanical engineering discipline. It's a skill that you really need to have, and it's not something that I'm going to lower the expectations for. Okay, this is very important, so please, by all means, pay attention to this subject. I hope you guys have a great day.